Assalamualaikum and good morning, and I welcome you all to the second cycle of microteaching. Okay, I would like to ask you, before I start the presentation, I would like to ask you, do you guys know what is the most prestigious award in sciences?
No.
Yes.
Nobel Prize?
Yes, Nobel Prize. Okay, good. Okay, do you guys know to whom and when it was given first time in the discipline of physics? No. Okay, no problem. I give you a clue. Okay, what is this? Ring. Okay. Do you see only ring?
Stone.
There's a beautiful hand as well. Okay, I give you a clue to whom it was given. Okay, what is this? X-rays. So the topic of my presentation today is on X-rays. And the first Nobel Prize was given to the guy. He was from physics, and the Nobel Prize was given on X-ray because he detected X-ray and he produced these X-rays for medical and for other purposes as well. So we go to our presentation. The content of my presentation is, first of all, we have outline. In the outline, we will go through background, which will be covering the general information about X-rays. And then we will move to the principle of X-ray production, which is Bremsstrahlung effect. Means whenever a fast-moving charge is decelerated, it produces X-ray. So we'll go through these, and then we will move to X-ray tube. How X-rays are produced in an X-ray tube. So we'll go through video as well, where the concept will be more clear. The objective of this presentation is to understand X-ray production from X-ray tube. And the learning outcome is that at the end of this presentation, you guys must be able to understand how X-rays are being produced from an X-ray tube. So first of all, in the background, X-rays were discovered by Wilhelm Röntgen. He lived from 1845 to 1923 AD. And in 1895, he discovered X-rays. And the discovery of these X-rays bring him the Nobel Prize in 1901. And this was the first Nobel Prize in the field of physics that was given to Mr. Röntgen. Okay, for the nature of X-rays, X-rays are actually electromagnetic radiation. In electromagnetic radiation, we know that there are electric and magnetic fields. Both these fields are actually oscillating perpendicular to one another. For example, in the diagram below, you can see along the y-axis there is electric field over here, and along z-axis there is magnetic field. And the propagation of these electromagnetic waves is perpendicular to both these fields. This is the nature of electromagnetic radiation. And the wavelength of these X-rays are in the range of 0.01 to 10 nanometers, where 1 nanometer is 1 billionth of a meter. So this, the wavelength of these X-rays lies within that range. So these are very energetic particles. You can say photons of energy, very energetic. And the applications of these X-rays are in medical, for diagnosis, for detecting broken bones, airport security, and we also use it for material characterization. In material characterization, the wavelength, as you have seen, this is it's ranging from 0.01 to 10 nanometers. So this range actually is comparable to the interplanar spacing of the atoms. So when these wavelengths are comparable, we can identify what is the interplanar spacing of atom, and from there we can detect what atoms are present in a material. So it's similar, it's analogous, like we have thumb imprints. We can detect identity of a person, and in a similar way, when we use X-rays for different materials, from there we can find the interplanar spacing of the atoms, and we can detect what atoms are present. So that's how we use X-rays in material characterization. Basically, material characterization is my field. My PhD is in nanomaterials, so I have used this X-rays also as well. Okay, the principle of production of X-ray is based on Bremsstrahlung effect. What is Bremsstrahlung effect? Bremsstrahlung effect is actually in real world, in our daily life, we can see, like, we can compare it to a fast moving car. Whenever it is stopped, either by accident or when you apply brake, the energy is transferred either to the frictional energy between the tire and the road, or if it has an impact with another car, another vehicle, the energy will be transferred to another vehicle. But in the atomic world, whenever a fast moving charge particle is stopped by a nucleus, its energy is emitted in the form of photon, or quanta of energy. So this quanta of energy, whenever a fast moving fast moving particle is decelerated, having wavelength within the range of 0.01 to 10 nanometers, this quanta falls in the range of X-rays. So that's how the X-rays are being emitted, by deceleration of fast moving charge particles. There are three different scenarios. For example, here we have, it's not working. Okay, we can just go through. We have three different scenarios. In number one, we can see where the fast moving charge particle has direct impact with the nucleus. In this case, the amount of energy emitted is very high. You can see the maximum energy is emitted. In the second case, the interaction is very close, but it's not direct impact. So the energy emitted is relatively less. And in third case, it has a very distant interaction with the nucleus, so the energy emitted is even less than the second case. So that's how these X-ray radiations are emitted. And this is the X-ray tube, our third part of the presentation. In X-ray tube, we have cathode. On the left side, you guys can see cathode. Cathode actually emits fast-moving charged particles, which are required to produce X-rays. These electrons are directed to the anode, which is a heavy metal. When these electrons strike this heavy metal, X-rays are produced. And we can set the angle of this anode in such a way that we can control the direction of the X-ray produced. And at the back of this anode, there is copper rod. Copper is very good thermal heat dissipator. And because in this process a lot of heat is involved, and this heat is actually carried away by this copper rod. So at the back we have a chiller type arrangement. So this water moving chiller actually cool down this anode material. So that's how the X-ray tube works. Then I have a video to further elaborate how this works. There is a sound problem actually, but you guys can see. There is labeling as well. This is tungsten filament. And when we apply a potential difference across these electrodes, a beam of electron or cathode rays are emitted from cathode and they are targeted to the anode. The function of molybdenum cylinder is we give it a negative potential. So this negative potential actually repel electron, and these electrons can be directed to the anode. Very precisely, it's like a pencil cake like shape, and they are very directed on the anode. And from anode they are decelerated. Because of this deceleration, the Bremsstrahlung effect, they produce X-rays. And we set this angle at 45 so that the X-ray produced, they come down, and we can obtain these X-rays through the window. And at the back you can see the water is moving and it's continuously cooling this copper anode. here you can see the X-rays produced. Because of the angle of this anode, we can easily control the direction of produced X-rays. And with increasing the intensity of the number of electrons, we can increase the intensity of the X-rays produced.